I know you have other classes, but at least break from my classes, right?
Sure.
Okay, so last couple of lectures you guys have learned filters, different kinds of filters, right? Especially the convolution filters. And we've looked at, like Gaussian, Laplacian, okay, gradient filters, and so on. Okay, so hopefully you guys have a good idea of, given a type of need, okay, given a type of need, what kind of filter would we create? For example, if we wanted to remove high frequency noise, what's a good filter? Gaussian will be a good choice for that, right? Okay. Anyway, if we wanted to create a high pass filter, you have seen, if we do I minus L, then we can create the kernel for any kind of filter that we want, right? Okay. So then we also saw, for example, if somebody gave you a kernel, let's say, -1, -2, -1, 0, 0, 0, 1, 2, 1. What does this kernel, what will this do?
Oh, this is derivative.
It's a first derivative type of filter, a gradient type of filter. So will it enhance the edges and
this edges it will enhance it
in the x direction, right? Okay, so same way if I made it the -1, -2, -1, 0, 0, 0, 1, 2, 1. So this will enhance the edges in the y direction as an example, right? And if we did ix squared plus iy squared, so if ix is the derivative in the x direction plus iy squared is the derivative and took the square root, then what filter do we get? No, the gradient filter. Okay. So anyway, based on the second derivative, we saw how the Laplacian filter can be created and what's the kernel for it. Okay, then if you recall, we looked at we looked at in the last lecture canny edge detection. And you guys saw how the algorithm goes, and whatever the object is, if there's a table over here, it will basically zero out everything else and just give us the outlines. Everything else will be darkened. So it's like a binary type of filter, so that we can just focus on the edges. And we went over the details of the algorithm, and internally you guys saw how it used the gradients and so on. Okay, so very similarly, today we'll take a look at another important need that arises in many situations, and that's called the corner detection. Okay, so if you're given some kind of an object, okay, so for example, let's say you're given some kind of integrated circuit, okay, which looks, okay, and so here somebody else gave you another picture of an integrated circuit that looks like this, and then internally, okay, for those of you who have done some VLSI design would remember there's a lot of
gates and transistors.
Layout, so let's say we did an X-ray image of 2 computer chips. And the idea was to determine which one is real, which one is fake, because these days there's a lot of theft going on, IP theft. So if your company did a design and somebody else stole the design, and now they also created the chip. So typically what we'll do first is try to align the 2 images before we do anything, before we take a look at the internal detail. So aligning 2 images, basically means make them same size and rotation. Okay, before we do any further analysis. So let's pretend the X-ray camera or X-ray vision system took an image of our computer chip. Then here's another X-ray vision of another chip over here, correct? Whatever it looks like. So it's slightly, as you can see, a little bit turned. So there's a rotation involved over here. The size is different. So like I was saying, the first thing we'll try to do is make this one as similar in size, similar in rotation to this one, before we go inside and see what are the differences between the two. Okay. So that aspect where we have a reference image. So in this case, this is our reference image. Okay, this is the given image. Okay, and our goal is to rotate, scale, shift given image to become as close as possible to reference image. And this concept is called, in the computer vision field, image registration. So next couple of assignments that you will be dealing with will be learning what are the techniques for image registration. Okay. As you will see, one of the fundamental prerequisites to be able to do image registration is locating correspondences between two images. Okay, what I mean by correspondences is, let's say we have a point over here. So the left corner point as an example. Okay. If we know where exactly is the left corner over here, then that's a correspondence, meaning this point corresponds to this point. Okay. Very similarly, let's say I have this point over here. Which should it correspond to? The lower point. Okay, so if we are able to determine more than 2-3 points where we know exactly, this was an example of an integrated circuit, but it could be a car or something. Let's say here's some kind of a car. Here's another picture of a car, but a lot smaller. Okay. So for example, we may be interested in, okay, what is the equivalent of this point in this image? Then obviously it has to be this. What is the equivalent of this point on this second image? As you can see, it has to be this. So one way of knowing the correspondent, or let me backtrack. If we know the correspondences, as I will show you, we can set up a mathematical equation to align the two images fairly easy. Okay, and we'll go over the math, how that works. But the prerequisite, like I said, is we have to know the corresponding points. Okay, so one way to do that is through corner detection. So let's say it's a square type of image or rectangular type of image. So if we can detect the corners over here using some kind of technique, detect the corners over here, then we can establish correspondences between the corners, and then go to the next step of mathematically figuring out how much do we rotate, how much do we scale, how much do we shift this particular image to make it look similar to the target image. And of course, then the next goal is, after we have aligned, then what do we do? How do we know whether they are similar or not? So we need another criteria for the similarity measure once we have registered the two images. So we'll go over all that mathematical background, how do we accomplish these things. But anyway, so first let's take a look at corner detection. So one of the famous algorithms for corner detection is called Harris corner detection. So I'll go over the algorithm. As you will see internally, it uses some of the convolution filters that we talked about, okay, especially the horizontal gradient and the vertical Sobel filter as an example. Okay, so the fundamental idea is pretty easy. Okay, let's say you are given some table. Okay, with some legs or whatever, right? Okay, so in the Harris corner detector, what we do is we create a small window. For example, this could be 10 pixels by 10 pixels. Okay, so here's a small window. Okay, then what we try to do is we'll move the window a little bit in the x direction, a little bit in the y direction. So delta x, delta y. And we compare. Before we move, what was the x gradient, meaning gradient in x direction. Okay, and as we move, what happens to the gradient in x direction and similarly in y direction. Okay, so let's pretend the table is blue color. So everything is blue over here. So if I move this window a little bit to the left or a little bit down, will the gradient change?
No, because it's blue.
So it's all the same color. Remember, the gradient basically becomes higher when there's a sudden change, right? On the other hand, let's say our window is over here. Let me remove the legs for the time being. Okay, let's say here is our window. Okay, now if I move the window in the x direction, will the gradient change?
No.
No. But if I move the window in the y direction,
Yes. Yep.
the gradient will change, right? So now you get the idea. If you have some kind of a corner, right? And if I put the window over here, will the gradient in both x and y change?
Yes.
If we are on a corner?
Yes.
So that's the fundamental idea of the Harris corner detection, right? So let's go through the algorithm. I picked up a PowerPoint from another university, which is very famous. Everybody else references that. So let's go through their explanation and see if it makes sense. Okay, as we go through the PowerPoint, okay, there's another concept we will need. So let me clarify that concept so that we can look at that. Okay, so we need a concept of eigenvalues and eigenvectors. So we'll be dealing with these also in the next couple of assignments. So let me refresh your memory, or in case you haven't come across it, let me give you the calculation and also the intuitive meaning of it. What do they do, right? Okay, so let's say you are given some matrix. Let's say A equal to 2, 1, 1, 2. Okay, so as you can see, this is a 2 by 2 matrix, right? So basically, an n by n matrix will have n eigenvalues. So if it's a 100 by 100 matrix, how many eigenvalues will it have? 100. Okay, if it's a 2 by 2 matrix, 2 eigenvalues. Okay, next question, how do we calculate those eigenvalues? Okay, the formula for calculating the eigenvalues goes like this. Take the determinant of lambda I minus the matrix and set it equal to 0. And lambda are the eigenvalues. Okay, so let's go through this very simple example. So if I is the identity matrix, okay, not the identity in terms of the images, but identity in terms of the matrices.
Yeah.
So in terms of the matrices, this will be correct? Minus A, 2, 1, 1, 2. And now we need to take the determinant and set it equal to 0. Okay, so as I multiply a matrix by a scalar, every value becomes lambda, lambda, 0, 0, right? Then if I do minus this one, as you can see, this will become lambda minus 2. Minus 1. And minus 1. Lambda minus 2. And now I need to take the determinant of it and set it equal to 0. So the determinant will be, as you can see, lambda minus 2 squared minus 1 equal to 0, which is lambda squared minus 4 plus, actually plus 4 minus 1 equal to 0. So this becomes lambda squared minus 4 lambda plus 3 equal to 0, right? Which is basically lambda minus 3 lambda minus 1. Correct? So then lambda 1 becomes 3 and lambda 2 becomes 1. Okay, so those are the two eigenvalues. Okay, so these are the two eigenvalues corresponding to our original data. Okay, so then next concept, okay, corresponding to each eigenvalue. There's an eigenvector. Okay. The eigenvector will have a dimension n by 1 for a given n by n matrix. So vector is always like a column of numbers, right? Okay, so corresponding to lambda 1 equal to 3, there will be an eigenvector. Corresponding to lambda 2 equal to 1, there will be an eigenvector. Okay, so the next question, how do we calculate the eigenvector? The formula is AB equal to lambda B. Okay, so if I put A, which is 2, 1, 1, 2, B1, B2, pretend those are the two numbers representing my eigenvector. Okay, let me take lambda equal to 3, B1, B2. Okay, you guys agree? Okay, so now if I further go row by column, so the first row by column will become 2B1 plus B2 equal to 3B1. Okay, so anyway, if I go, for example, did I do it right? 2B1 plus B2 equal to 3B1, right? Yes. So anyway, if I now go B2 equal to B1, so one possibility for this eigenvector will be just 1 and 1, okay, or 2 and 2, or 3 and 3, whatever, okay. So that's, by the way, eigenvectors are not unique. We could have different eigenvectors, but anyway, one of the eigenvectors for corresponding to lambda equal to 3 will be 1 and 1, right? Okay, then if we do, for example, same thing, AB equal to lambda B for lambda equal to 1, so then this will become 2, 1, 1, 2, B1, B2 equal to 1, B1, B2, So in this case, this becomes 2v1 plus v2 equal to v1. So that, what does this become? Correct? If I subtracted here, this will become v1 if I took v to the other side, right? So one possibility will be what number?
1 minus 1.
1 and minus 1. So this is one eigenvector, and 1 and 1 is another eigenvector. So these two are our two eigenvectors. Okay, so because we'll be again using this concept later on, so let me clarify a few intuitive ideas over here. Okay, let's say this is our x and y. Okay, any point we have, let's say I have a point over here, x of 3, y of 2, let's pretend, are the coordinates, right? So remember then this point could be represented as 3, 2. Or in vector form, how could we write it?
For the x coordinate.
3, 2, right? Okay, so think of every point as, remember vector has a magnitude and a direction. So the magnitude of this vector will be from the origin to that point. So that's basically our 3, 2 vector. Okay, the angle will be tan inverse y over x. So the angle will be tan inverse y over x. So in this case, whatever, 2 over 3. Okay, and what will be the magnitude?
Root of 6 component.
2 square plus 3 square square. So x square plus y square
Yes.
square. Okay. So sometimes, as we are especially dealing with computer vision, we need to know a unit vector in a given direction. Okay. A unit vector will always have a magnitude of 1. Okay, so how do I convert this vector 3, 2 to unit magnitude? All I have to do is divide 3 by the magnitude and 2 by the magnitude. Okay, and now if you try to compute the magnitude, you will see it will come out to be 1. Okay, so coming back over here to the eigenvalues and the eigenvectors. Eigenvectors basically give us a direction. Okay, let's assume the magnitude is 1. Okay, if the magnitude of the vector, even if the magnitude is 1, see this represents a point in two-dimensional space, right? So as you can see, if this is x, this is y, x of 1, y of minus 1. So this particular vector will be pointing in this direction, right? Do you guys agree?
Yes.
And what about 1 and 1?
Towards the positive x-axis.
It will be pointing at the 45-degree angle.
Yes.
Okay. Okay. So eigenvectors are often used, and as we go further into some of the practical applications, what you will see is, let's say I have some data as given to me. Okay, so this is some XY data. Okay, if we now compute, let's say, 2 eigenvectors, one of the eigenvectors will be pointing something in this direction. Because if you take a look, this is the, let me put some more points over here. Okay, most of the data is oriented this way. Okay, so one of the eigenvectors, if we computed the eigenvalues for this data corresponding to the eigenvalues we computed, computed the eigenvector, then one eigenvector will be pointing where mostly the data is oriented, right? And the eigenvectors are orthogonal to each other. So the second eigenvector will be pointing to the data where there's the next variation. Okay. So this will become more clear as we go through some examples.
Can you repeat it again, sir?
Okay. So if we are given some data, okay, let's say in the two-dimensional space, then it will give us basically two eigenvectors. Okay. One of the eigenvectors will be pointing in the direction of the data. So if our data is like this, okay, then one of the eigenvectors will be pointing in the direction of the data where the data has the most variance. Okay. The other eigenvector will be perpendicular to it, meaning, the next variation. So in the two-dimensional space, this is how it will, this is the information eigenvectors give us. In a three-dimensional space or higher dimensional space, so let's say we have a higher dimensional space. For example, 10 dimensions, even though I cannot draw 10 dimensions, right? Okay, so suppose we have 10 eigenvalues. Okay, now if we take a look at the highest eigenvalue by magnitude. Okay, let's pretend these were lambda 1.3, lambda 2, 1.2, so on. Okay, lambda 4. Okay, let's say 8.3, lambda 10, let's say 0.11. Okay, so let's say we sort these eigenvalues by magnitude. So in this case, let me assume 8.3 is the highest magnitude. Okay, now I create an eigenvector corresponding to the highest eigenvalue. So in the 10-dimensional space, this eigenvector will be pointing to where the data has the highest variance. Hopefully, as we go more into some real examples of this, it will become clear. Okay, so let's say the next highest vector over here is lambda 7. Next highest eigenvalue is lambda 7. Okay, if we compute the eigenvector corresponding to that one, then in the 10-dimensional space, that will be perpendicular to this one, which will basically be where the next variation occurs in the data. Okay. So eigenvalues, eigenvectors basically are very important in letting us know about the variation of the data. The highest eigenvector the eigenvector corresponding to the highest eigenvalue will tell us where there's highest distinction in the data or the highest variance in the data. Okay. Anyway, we'll be going over this quite a bit, so hopefully gradually you'll see it will start to make perfect sense. So let's take a look at the algorithm for the Harris corner detection. So let me just put it on the computer. Okay, so if you guys go to the website CPEG585, Okay. So under the handouts, okay, I have Harris corner detector over here. So it's a PowerPoint presentation from some other university, okay, which everybody else also uses. So even if you take a look at the OpenCV documentation, they have pictures from this handout. So anyway, this is what it looks like. It's from Penn State. Okay. So I see a misspelling over here, matching, I is missing. Okay, anyway, so the first couple of slides are very basic, and it talks about what are the important corresponding points, right? So for example, this one may correspond to this point, this may correspond to this point, so which we've already discussed, so this is pretty straightforward. Okay, if I go to the next one. Okay, so then they are talking about patches. For example, if this is one of the inputs given to us in one of the images, right? What's a proper match? Which patch matches this one? As you can see, it's basically this one, right? So basically this matches this patch over here. Okay. In some of the algorithms, we worry about matching the patches. So at that point, we will, but anyway, it's very simple concept. Yeah, same thing, nothing special. Okay, so here the author is talking about if we have to pick a patch, which patch is a good patch? Okay, for example, if we, in the source image, if we decided this to be the patch, then the problem is, you know, the background is same pretty much everywhere, so this will not be a good choice for a patch because our algorithm may match it here, may match it here, may match it here, so we may get very poor vision results, whatever our goal is, whether it's image registration or recognition, whether the two are same or not. So we won't be able to accomplish. So choice of a patch is important. Okay. So for example, will this make a good patch? Right? It's sort of a corner. Oh, actually, it is a corner. So yes, this will make a good patch so that we can try to come up with a correspondence somewhere else. Okay. Anyway, the basic idea, as we had discussed before, is, you know, if there's a corner, try to create a small window, then move it in the x direction, y direction, and see how do the gradients change. If it's a corner, then both x and y gradients will change. Do you guys agree?
Yes.
Okay, so then okay, here obviously if we move it in any way it will not change. Okay, let's pick this